video feeds on the screen, lots of faces. This is all very experimental and new way of running a conference. So a quick rundown, Barry already explained this. The way we do this is we have 10 minutes for the presentations. The presentations are pre-recorded. After presentations, we have 10 minutes for up to 10 minutes for questions and answers. The way we run this is that you can flag questions via chat, either to me or post them to everyone. You don't have to spell out the questions completely, because they are only for me there to prompt you to speak up and pose your question. So after each presentation, I suggest clapping is a bit difficult, sort of, you know, with unmuting and everything. So to acclaim speakers, I suggest we do it the German way. So briefly unmute with using one hand on the space bar and use the other hand to knock on the table. Maybe we can quickly try this out. Yeah, so everybody, fingers ready, unmute with the space bar and knock on your table. Okay, 1, 2, 3, go. It's very silent, so you have to knock a bit harder. Okay, well, let's see how it goes, but it would be nice to have a bit of noise for the speakers to recognize their presentations. But let's get going. First presentation up is by Elina Kuosmanen from the University of Oulu. And her work is entitled Measuring Parkinson's Disease Motor Symptoms with Smartphone-Based Drawing Tasks. So Elina, now it's over to you.
Okay, thank you. I will put the video on. Hi, my name is Elina Kuosmanen. I am from the Center for Ubiquitous Computing from the University of Oulu in Finland. I will introduce our study on measuring Parkinson's disease on smartphones with drawing tasks. Spiral drawing has been utilized for years as a clinical tool to observe tremors and other abnormal movements in the assessment of different movement disorders, such as Parkinson's disease. It is conducted usually on pen and paper and analyzed visually by a trained clinician. Hence, it's not utilized that often. We wanted to see if this could be conducted digitally using a smartphone, since smartphones are ubiquitous also among elderly. There has been attempts to digitize the spiral drawing on a tablet before using a stylus. We decided to conduct drawings with the finger to make the assessment available without extra equipment. We developed 2 drawing tasks. First, the spiral task, resembling the traditional task. However, when using the finger to draw, the line is hidden under the finger, making the drawing more difficult. So to minimize the effect of finger occlusion, we created another task, a square drawing. The square shape is more predictable and familiar, hence easier to conduct with the finger. Next, I will introduce the application we developed for the drawing tasks. Here you can see the spiral drawing task flow. First, the user sees the instructions. The spiral drawing is started from the center of the spiral. The drawing is made according to the given template, and when ready, user clicks done. The arrow is calculated as an average of the distances between the drawn line and the template line in each user drawn dot. In result view, the app provides the arrow, maximum arrow, standard deviation of the arrow, and drawing time. The square task is conducted in similar way. The square drawing is started from the bottom left corner. After clicking done, the app provides the same metrics as in spiral drawing. We conducted a user study with Parkinson's disease patients. The drawing tasks were tested by 14 test subjects in the local Parkinson's Association meeting. In the meeting, we introduced the study and collected consents. Most of the Parkinson's disease patients come there with their spouses, so we were able to recruit an age-matching control group. We got 8 participants with Parkinson's with mean age of 71.5 years, 4 males and 4 females, and 6 controls without Parkinson's with mean age of 72.3 years, 2 males and 4 females. We refer to these groups as PD and non-PD. All participants conducted 3 spiral drawings and 3 square drawings using the same device. We recorded the touch coordinates with the timestamps and the screen captures of the final drawings. We analyzed following metrics from the data: drawing speed and total drawing time. Drawing speed is measured in pixels per millisecond. We counted the average speed of a drawing and also a pointwise speed during the task. Drawing accuracy, the error is calculated in pixels as the average of the distance of the drawing from the template in each drawn dot. The crossing rate is the number of occurrences where the drawing line crosses the template line divided by the total number of drawn dots. Radial and angular velocity are counted only for the spiral task. Radial velocity describes how much the radius of the spiral increases in pixels per millisecond, and the angular velocity how much the spiral angle changes in radians per millisecond. We also studied the drawing sampling rate. Parkinson's disease might cause finger jumping on the screen, causing deviations in the touchscreen sampling and gaps in the drawing. We found out that the group with the Parkinson's disease had longer drawing time and slower drawing speed. On average, drawing time and speed are longer in both spiral and square task. And in spiral, the average radial velocity and average angular velocity are lower. The Parkinson's disease group's drawing speed varies more during one task, while drawing speed of non-PD is more constant. The differences in drawing speed and time are not statistically significant in our study, as it was in previous studies with the tablet. Since we are using a smartphone instead of tablet, we have a smaller screen size and hence smaller drawing estate and shorter drawing task. It might be the reason why the difference was not statistically significant with this sample size. In spiral drawing, average crossing rate of the group without Parkinson's was bigger, and the average error was lower. This means that the non-PD spirals were more compliant with the template. In square drawing, average crossing rate of the group with Parkinson's was bigger, and the average error was also higher. We can say that the non-PD drew closer to the template with straighter lines. And 16% of spirals and 16% of squares had gaps in the group with Parkinson's, and none of the spirals and 11% of squares had gaps in the group without Parkinson's. There were some unexpected things during the study. Some participants drew the square intentionally line by line, explaining the big amount of gaps in previous slide also for the group without Parkinson's in the square drawing. There were things challenging the error calculation. Another finger hitting the screen accidentally causes sharp straight lines and a big error rate. See PD5 spiral on the slide. Some drew extra rounds in the beginning or in the end of the spiral, like PD7 and non-PD1 spirals on the slide. Extra round in the beginning mixes the error calculation that utilizes the angle in finding the closest dot of the template. Some participants made corrections to the drawings by drawing another line closer to the template, as in the square on the slide. We asked feedback after the task. Generally, the feedback from participants with Parkinson's disease was positive. Half of them described the tasks as easy, but none of the other group used that word. The participants without Parkinson's told that the tasks were surprisingly hard and challenging. In future, we want to understand which Parkinson's disease symptoms affect the most the drawing performance. We will investigate whether we can detect and measure the medication effectiveness and lasting effect. We are planning to add additional tasks to assess reaction and memory decline and evaluate data and tool for clinical support for managing Parkinson's disease. We want to thank the Parkinson's Association of Northern Finland, local section of Oulu, where we could conduct the user study. And feel free to contact me or get familiar with our project or our research group via the websites. Thank you.
Thank you very much. Let's all thank Elina for her talk with a round of knocks. Make it loud. Okay, excellent. Excellent. We're getting better at that. By the end of this session, we'll be masters. For any questions from any of you, please use the chat function to make me aware of your question, and then I can call you up and ask you to unmute and pose your question. But I can start it off with a couple of questions. Elina, I was wondering, you mentioned that similar work had also been done with tablets.
Yes.
Which seems to make really sense, because a tablet would appear much more like a piece of paper on which I draw, as opposed to a smartphone. So can you say a little bit more about why the choice of a smartphone? What is the bigger vision behind that?
Yeah, we are creating this kind of a wider combination of tools for treating Parkinson's disease, and we want to go with the smartphones because they are so ubiquitous and they are always with you. So you could be conducting the symptom assessment wherever you are. For example, if you feel like now I'm feeling a little bit worse, you could track your symptom level wherever you are, where the tablet is normally not taken with you from the home.
All right. Maybe a follow-on question to that. Typically, or very often, we use phones more like, also as you showed on the slide, as held in one hand and then using the other hand to provide input. But that would seem to be potentially more difficult or more challenging than having a tablet or a piece of paper on a solid surface. So how was that reflected in the study?
Well, we didn't instruct the users anyhow how to hold the device. We were giving them the device, but of course, normally you always take the smartphone into your hand, so they were conducting. As you saw maybe in the slide where there were some examples from the drawings, another finger was hitting the screen accidentally for especially one participant who had that issues. So we have considered some design implications towards that, so that maybe we could reset the task in some circumstances, for example, lifting the finger, or if we could detect this kind of another finger hitting somehow. But this might cause the task to be really difficult to complete with the Parkinson's, since the 17% of drawings by Parkinson's participants contained this kind of breaks in the drawing, whereas only 5% of the control group had the breaks. So if we always reset the task when there's a break, it might be really difficult to complete. So maybe we should just make the error calculation better and take somehow into consideration these issues.
All right. So I haven't seen any other questions, so I keep going. But if any of you have questions and for some reason they don't show in my chat, maybe just wave wildly in your video feed. But I was wondering, so this drawing task is one of, I assume, many different diagnostics that get used for Parkinson's symptoms. So can you give us a little bit more of context about what other kind of tests might be possible with smartphones?
Well, we have created, for example, this kind of ball game where you hold the device slantwise and try to keep the ball in the middle of the screen. So we are tracking the accelerometer during that game and try to detect tremor from the accelerometer signal. And of course, we can use many kind of self-assessments, and we have built a medication journal where we are tracking the medication intake time, so we could maybe see the medication effect, or how long does it last if we conduct these measurements after the medication regularly.
Right. So, thank you. Right. So if there's no other question, then suggest we thank Elina again. All right, thank you. Big knock.
Yes.
Okay, so we have now 3 minutes before we start the next talk. So we can just have, you know, 2-3 minutes break. We keep in sync with the session slots, just so in case people want to switch between tracks. So a mini break, 2 minutes of silence, and then we'll have the next presentation by Jens Emil.
And while we're taking this break, can I just jump in and say that one of the other tracks has been Zoom bombed. So to keep us a bit safer, there'll be a couple of us here taking people off. They get a bit dodgy. But for the speakers, when you share your screen, if you can click the little more button on the bar that appears, and then disable annotation, because apparently when we stopped letting people share their naughty things, they decided to draw naughty things all over the slides. So when it's your turn to share your screen, if you could just go in there and disable people being able to draw on your slides, that'd be great.
Thank you. Very good. Thank you, Donald. Okay.
So does that mean when I share my screen, I should disable something right after sharing?
Yes. So once you click the share screen button, you get the little bar with all the stuff on it, with all the controls, and there's a more button there. And in your menu, you have disable annotation for attendees, which just stops them drawing rude symbols all over your slides.
Great, thanks.
I have a comment in chat from Yo, who cannot unmute himself because one of the hosts muted you.
You should be unmuted now.
Should be unmuted. Okay. Okay. All right.
I don't know why I have
got it.
Okay.
All the presenters are hosts, so that you can share your screens.
Yeah.
So
okay, Joe, give us a quick knock. Oh yeah, good. All right. Okay. So we're coming up to 10:02. Okay. Ready for, you know, Danish punctuality. So next talk up is by Jens Emil Grønbæk from Aarhus University. And Jens Emil will talk about proxemics beyond proximity.
Hi, I am Jens Emil Grønbæk from Aarhus University, and this talk is about proxemics and cross-device interaction. The research is done in collaboration with co-authors Mille, Peter, Jo, and Marianne from Aarhus University, and Kenton from Microsoft Research. Designing for flexible use of space is one of the key challenges when supporting co-located collaborative work, and it is among the core interests in research on cross-device interaction. Today's mobile devices, for instance laptops and smartphones, enable groups of people to arrange in many different configurations around a table. But they currently also lack support for spontaneous sharing across devices. And this constrains our flexibility in social interaction. To address this problem, we present a design perspective for supporting flexibility, and we demonstrate it via 3 prototypes of cross-device interaction. Slam to share for content sharing by slamming the table, stick to share for content sharing via interactive stickers, and finally show to share for control sharing by showing QR tags on screens. Several prior systems for cross-device interaction draw upon Proxemics for detecting proximity, but we demonstrate a different approach to Proxemics beyond proximity detection, where we specifically focus on key insights in the theory for supporting flexible use of space. Proxemics theory sensitizes us to the interplay between people and artifacts, and through this lens we consider not just the technologies themselves, but how they work together with the physical environment to frame social interaction. I'll first talk about how Proxemics has been adopted previously and what is new about our perspective. I'll explain our research approach, and then I'll focus on the design of one prototype, Slam to Share, to show that our perspective is operational for design. We contribute 3 design sensitivities, and I'll focus on how Slam to Share addresses each one of them. As I mentioned earlier, research on cross-device interaction often draws upon Proxemics theory. The theory originates from Edward Hall, and it is the study of how people use space to enact social relations, for instance through interpersonal distance. It has inspired a framework for Ubicom systems known as proxemic interaction that focuses on detection of spatial relations between people and devices. Generally, the approach is to enable cross-device interaction by detecting aspects of proximity, such as patterns in distance and orientation. Often the systems also rely on fixed external sensing infrastructure. Now, we argue that proximity detection in this way also constrains flexibility in social interaction. In contrast, we pose the question, how can Proxemics inform design of cross-device interaction to support flexible social interaction? Proxemics theory, in fact, contains important insights when it comes to designing for flexibility. We highlight 3 insights that have received less attention, in particular for design of cross-device interaction. These have been identified in the literature, but are also based on the design research we have done. Our contribution is to highlight these aspects of Proxemics as design sensitivities and demonstrate through proof of concept how to operationalize them. Before explaining the design sensitivities, let me briefly explain our research approach. We have focused on the process of designing, following the tradition of research through design, where designs are informed by theory and empirical observations. So a small disclaimer, this is not your traditional system plus user study. Instead, we have developed design sensitivities through the integration of empirical, theoretical, and experimental work in the following way. We conducted a field study in an open space for student group projects, analyzing their collaboration practices through the perspective of Proxemics. This has informed several design experiments with prototypes of cross-device interaction techniques. In the paper, each prototype exemplifies how to adopt each of the sensitivities for designing interactions, but for the talk I'll focus on Slam to Share. In the paper, we use Edward Hall's terminology of fixed and semi-fixed features for describing shared physical space. For instance, a wall is fixed, whereas a table is semi-fixed because it can be moved. This distinction is useful in understanding the properties of different artifacts when it comes to enabling and constraining social interaction. We can observe, for instance, that the table is a semi-fixed feature of group work that has certain consequences for sharing. The table surface enables placing our laptops on it, like shown here, but it also constrains how we can view contents together. For instance, here a student must rotate the laptop away from himself for the rest of the group to see the screen. The idea of Slam to Share is to exploit the social meaning of the spatial relationship between people, devices, and tables. The devices running Slam to Share jointly detect 2 consecutive slams on a table surface, and this sets up a digital sharing relationship between the devices. Let's see it in action. So in this scenario, Alice, Bob, and Eve want to share a slide deck to start collaboratively editing a presentation. Their individual phones and laptops are connected via their personal user accounts, but they still need to establish a connection across each other's devices. Alice creates a slide deck. They all place their phones on the table, and as you saw, Alice can pound the table twice to establish the connection. Now they all have access to the same document and can start editing it on their laptops. Now this was the basic interaction. I'll now explain the details in the interaction design to illustrate our design sensitivities. The first design sensitivity is to incorporate fixed and semi-fixed features of the environment. Slam to Share incorporates tables in the interaction technique, and this way the table defines the bounded area for sharing. The second sensitivity is to enable flexibility in interpersonal distance and orientation. And notice in this clip how Bob can move away from the group space while his phone is still opted in. This shows the flexibility of action when the sensing is based on explicit interaction with the devices and not implicit detection of distance and orientation between people. Finally, the third sensitivity, support multiple alternative manipulations with the same effect. Essentially, it means that a system can enable multiple physical ways of interacting to achieve the same outcome. Slam to Share, for instance, supports 2 distinct ways for users to opt out of sharing. Bob from the scenario can move between different group tables for sharing, and opting out here is supported simply by picking up the phone from the table. But you can also opt out by flipping the phone face down. And supporting these alternative ways of interacting enables users to opt out while having the flexibility to sit and move in the way that suits them. So those were the 3 design sensitivities demonstrated via Slam to Share, and in the paper all 3 prototypes address each of the design sensitivities. So as a small appetizer for the paper, here's the argument with Show to Share. It supports control sharing for presentations via QR tags, and changing the size of the QR tag shifts the distance from which it can be scanned. This supports variability in the social spatial configurations of presenters and audiences. It also supports multiple alternatives by providing different ways of showing the QR tags, depending on whether you want to share only with the co-presenters or with the large audience. And this leads to my conclusion. We have shown how to operationalize proxemics beyond proximity detection. While the concept of proxemic interaction is focused on detecting spatial relations, we have demonstrated a different perspective focused on enabling flexible social-spatial relations. I've demonstrated our contribution of 3 design sensitivities via examples from the paper. For instance, in Slam to Share, relations between people's devices are defined by the boundaries of a table. In this interaction, people can flexibly organize themselves with different distance and orientation depending on the situation at hand. And we've seen 2 examples of how multiple alternatives for the same action also enables more flexibility in the user space. For more details and examples, please read the paper. Thanks for listening.
Applause, please, for Emil. Okay. Let me check the chat. I think we've got a question from Lars-Erik. Lars-Erik, you. Hi, Lars-Erik.
Hello, how are you all? Yeah, this is Lars-Erik Holmqvist from Northumbria University in Newcastle. Thank you for a great presentation. It's nice to see this work continuing with the whole problem of near field or close contact collaboration. However, today we're in kind of the opposite situation. So I was really curious how we can sort of somehow, I don't have the answer, so this is more of an open question, but how can we learn from your research in how people interact together to adapt that to how we will probably be interacting for a long time, which is either through video link or in at least a kind of a social distancing position. So I'd be very interested to hear that.
That's a very, yeah, that's a thing that has to be addressed when we are sort of, you know, it's interesting. Most of my research is, in my PhD at least, is revolved around, you know, co-located collaboration and all these scenarios of, and really, you know, yeah, focusing on, as this work shows, how flexibility is super important in how we engage with each other, but actually, as a sort of sidetrack to a lot of the ideas I've come up with, I've also been reflecting on, you know, remote collaboration, because one of my supervisors, who is also co-author here, Kenton, he is, you know, we're collaborating remotely, and you know, a lot of the same sort of, no, not the same, but there are a lot of issues with flexibility as well in these video conferencing systems, that we also, I mean, really could start to address through interaction design. Like, I think one of the really interesting potentials of all of us having multiple devices at hand is that we could, and like each one of them would have a camera typically, to also start to think about how can we better facilitate, you know, bringing multiple video streams in from one individual or several individuals who are together, and bring that into a remote meeting. For instance, it would be great if I could turn on the smartphone camera of my phone right now and point to some notes I had, for instance, or do a drawing here, or even if I had, you know, some physical artifacts I wanted to bring in. You know, we're very limited by having only this sort of talking head feed for mediating that interaction. So yeah, I think there's a lot of challenges of flexibility that we could sort of try to address in a remote collaboration scenario as well.
Yeah, we have another question from Yang Li. Yang, do you want to step up to the microphone? Yang, can you unmute? All right. Yang cannot unmute, so I will, or microphone doesn't work, so I'll read out the question. So Yang is asking if methods applied in your research, if you've thought about applying security features into these methods to you know, so that connections that people make between their devices are protected. Is this something you've thought about?
Yeah, I think it's one of the interesting trade-offs between, you know, setting up the pairing mechanism through some means of you know, more sort of direct proximity detection, like distance between people, for instance, or contact between devices as a sort of very close proximity measure. That, you know, the closer that your system requires the devices or people to be together, the more secure your mechanism is in a way. So there's sort of an embodied trust happening in the interaction. Whereas in that same trade-off, it also compromises the flexibility of action. For instance, like one of the scenarios we talk about in the paper is presentation situation, not one like this, but in a co-located setup where there's a presenter at a large screen and there's an audience sitting sort of slightly far from the big display. And in that interaction, if you had to walk all the way up to the screen to connect with it, to put up a picture in order to ask your question, there's a sort of high social cost of that physical transaction. Whereas if you could just do it from a distance, it would give you a lot more flexibility and maybe sort of even empower you to even participate and ask questions. So I think, as we articulated in the discussion of our paper, is really a trade-off of what is sort of the core thing you're trying to do, and that's also why we're suggesting in our perspective to consider which sort of social spatial relation do you want to enable with your system first, and then you can think about how that informs the design of your detection mechanism.
Right.
I hope that answered the question.
Yes, Jiang, I believe it answers Jiang's question exactly, sort of why not everybody has to engage at the same time in the SLAM, and why you want to provide more flexibility. Can I follow up just with sort of a technical question, more out of curiosity, how the SLAM is actually implemented in terms of sensing and how that works?
Right. So it's what's kind of interesting across all the three prototypes that we prototype concepts we present in the paper is that they are completely based purely on mobile built-in sensors in mobile phones. And I thought like one of the interesting things about the design exploration we did is that it's quite expressive what you can do just with that setup without relying on external sensing infrastructure, which is done in a lot of the related work. Specifically for SLAM to share, we're using the accelerometer, of course, to detect SLAMs in the table surface. And so when all the devices jointly detect two consecutive peaks in a small data window, so basically detecting a synchronous gesture, all devices will set up a pair. And interestingly, to also explore this notion of flexibility, we use the gyro to enable different variations of that interaction. So the gyro at first is used to make sure that the devices are steadily horizontal on the table surface, so you can't sort of opt in by just holding the device in your hand because of the jitter and also the slight orientation difference. And the other thing we're checking when it's on the table surface is whether it's face up or face down. And we also talked about that. I talked about that mechanism in the talk that also allows you to sort of maintain within proximity of others, but opt out. Right. So really the focus here is flexibility in how you engage with others.
Thank you very much. I think we have there might be more questions, but we really have to stop here to begin and hand over for the next talk. So let's thank Jens Emil again for his contribution. All right. So we have one more talk in this session. Just waiting for my clock to tick over to 10 past. Xinhui, if you want to get ready and bring up your slides. Yeah, let's just wait. Oh yeah, it's ticked over to 10 past. So we're in sync with the other tracks. This presentation is on eye and finger movement during mobile typing on smartphones, and it will be presented by Xinhui Jiang, who's from Kochi University, but I believe conducted this work with colleagues in Finland. So over to you, Xinhui.
Hello everyone, I'm Xinhui Jiang from Kochi University of Technology, Japan. Today I'm going to present a study about typing behavior on mobile devices, especially about eye and finger movement. This is a collaborative work between the user group of Aalto University led by Professor Antti Oulasvirta and the Center for Human Engaged Computing of Kochi University of Technology, led by Professor Xiangshi. As we all know, we use mobile devices every day, but have you noticed how you type on your smartphones? Many of you may think that typing on a mobile device is similar to typing on a physical keyboard because both of the devices have a quadri layout. However, the operations differs dramatically because of the smaller size and a lack of tactile feedback. First, there is no enough room for using 10 fingers on a soft keyboard. This means that the touch typing system cannot be applied on this device. And since there is no standard instruction for mobile typing, the users have to develop their own typing strategies. Second, apart from typing, the hands are also used for holding the device. This sets limits to the finger movement, especially for the thumbs. Also, because the keys are really small and hard to locate, the user have to frequently check them before clicking. So the studies about mobile typing showed extensive results on the typing performance, including the typing speed, error rate, and so on. They also analyzed the touch behavior, which contributes to the touch point autocorrection. At the same time, the softer strategies like how to balance their speed and accuracy and how the errors were corrected were also investigated. However, as we discussed before, typing on a soft keyboard relies on visual guidance, and the user's behavior relates to eye and finger movement is not fully understood.
Xinhui,
From the perspective of attention and the finger movement, we would like to discuss what is the difference between one finger and two finger typing, and how do the movements relate with
Xinhui, many of us can't see the video rolling, so you might have to start the presentation again.
Okay.
Did anybody see the video play out, or is this?
No, I think the wrong thing was getting through.
Can you see my screen share?
We can see the title slide, but it didn't begin to play.
Hello everyone, I'm Xinhui Jiang from Kochi University of Technology, Japan. Today,
the audio plays, but the video doesn't roll. The audio plays, but the video doesn't roll.
I think it's working this time because we can see the talking head at the top.
Okay, yeah, all right, thank you.
Okay, so I will.
Sorry for that.
Going to present a study. Hello everyone, I'm Xinhui Jiang from Kochi University of Technology, Japan. Today I'm going to present a study about typing behavior on mobile devices, especially about eye and finger movement. This is a collaborative work between the user interface group of Aalto University led by Professor Antti Oulasvirta and the Center for Human Engaged Computing of Kochi University of Technology led by Professor Xiangshi. As we all know, we use mobile devices every day, but have you noticed how you type on your smartphones? Many of you may think that typing on a mobile device is similar to typing on a physical keyboard because both of the devices have a quadri layout. However, the operations differs dramatically because of the smaller size and a lack of tactile feedback. First, there is not enough room for using 10 fingers on a soft keyboard. This means that the touch typing system cannot be applied on this device. And since there is no standard instruction for mobile typing, the users have to develop their own typing strategies. Second, apart from typing, the hands are also used for holding the device. This sets limits to the finger movement, especially for the thumbs. Also, because the keys are really small and hard to locate. So the studies about mobile typing showed extensive results on the typing performance, including the typing speed, error rate, and so on. They also analyzed the touch behavior, which used the touch point autocorrection. At the same time, the softer strategies like how to balance their speed and accuracy and how the errors were corrected were also investigated. However, as we discussed before, typing on a soft keyboard relies on visual guidance, and the user's behavior relates to eye and finger movement is not fully understood. From the perspective of attention and the finger movement, we would like to discuss what is the difference between one finger and two finger typing, and how do the movements relate with the typing performance, like speed and accuracy. So we introduced the study on mobile typing. First, we built a synchronized tracking system for finger movement, eye movement, and typing events with the tracking devices and a smartphone. We asked the participants to transcribe the sentences using 2 thumbs and the index finger. The sentences were translated from the EROM mobile email database, which is based on everyday conversations and easy to remember. We upload this experiment data as how we type mobile dataset for open access. You can find it on our project webpage. With this data collected in the experiment, we are able to rebuild the typing behavior in detail and conduct many analysis on the eye and finger movement. So we measured typing behavior on each of the aspects and reported the difference between one finger and two finger typing. For details, please refer to the paper. So first one, we assume that attention is one of the major differences between typing on a soft keyboard and on a physical keyboard. The data also supports that. Here we compare with the physical keyboard typing study conducted by Anna Veit and published at CHI 2016. On average, 60% of attention was located on the soft keyboard area in the two-thumb typing, while the number is 20% on the physical keyboard for touch typist, which is less than on the soft keyboard. And during typing, the users have to observe that this happens more frequently on the soft keyboard than on the physical one. And sometimes this attention shift can be affected by typing errors. Here are some examples of eye and finger movement areas described as heat maps. The pictures were selected from different participants typing the same sentence, but in different conditions. The left pair of pictures is for one finger typing. The right pair is for two finger distribution of key points. We can see that more attention was on the text input area on the top when the error and the error correction happens during typing. As for the difference between one finger and the two finger typing, we observed that users are more likely to focus on the keyboard when they typing with one finger. And we can see it in the left bar chart. the trend stays the same between the sentences typed with and without backspaces. And for attention shift, there is also more shifts in one-finger typing. Generally, the eye seems to be more busy while using only one finger for typing. As for the finger movement, we report the finger key distance. This is measured as the distance between the finger to move and the key to press at the moment of the last key pressing. For example, when we are typing the word hi with 2 thumbs, the finger key distance is the distance between the I and the right thumb, as the picture shows, when the left thumb is pressing H. But if we type with only one finger, the finger key distance is the same as the distance between the keys, because there is only one finger to move. Generally, 2-finger typing has the advantage of shorter finger movement distance. Now, let's talk about visual guidance. We observe target key. We assume that as a similarity, so we measure this similarity of movement path between the index finger and the eyes, and try to catch this coupling phenomenon. We found that when the user types faster, the eye and the hand follows last.
Hello,
And also more
my
coupling
video?
is related with more attention on the keyboard.
I'm sorry, Xinhui. Did you stop the presentation or?
Yes, I stopped the presentation because someone is saying that the slide is always at the second slide, so the video is not going on. Is that correct? Or
Yeah, it has partly moved on, but it just seemed to get stuck. Yeah, yeah.
so let me.
But we heard the audio continuously, so maybe you can. I don't know whether it works to start it at on a later slide.
So can I continue?
Yes, yeah.
From this, we can see that the close finger guiding during this key searching slows down the typing speed. So the experienced and fast typist who knows the key locations doesn't do this so much. There are so many details for us to discover with this dataset. For example, the key locating behavior before clicking on the keys. So looking at this green line in the picture, we are able to observe that the key is closer before the participant click on the space key. So now we know that attention is a precious resource during the typing process. We still have one question: how the 2-finger typing posture can reduce this attention on the keyboard. We now can give 3 explanations for this. The first one is after adding one more finger on this typing behavior, each finger controls fewer keys. So a better finger key mapping helps reducing this attention on the keyboard because they don't need to check every time they click. Second, fast typing speed with 2 fingers leads to more errors.
Xinhui, I'm afraid we've lost your video now.
I can send my video link in the chat.
Yeah.
Is it helping?
Antti has shared the video link.
Okay.
Okay.
Yeah.
So I have downloaded the video. I can play from, if you give me a bit to start from, I can play your video from there and see if people can see it that way. So when do we want to start?
Start from the a little bit. Yes, here. This
Here,
page.
okay.
Now we can't hear the sound. Don't you?
You can't hear the sound. Okay.
You have to share computer sound when sharing screen. It's a box you have to tick. So, but maybe you can do it from the more options.
Yeah, I thought I had. Here we go. Maybe it's on again. Let's try again.
This speed accuracy trade-off. The users have to proofread them during this error correction process. The third is that a better control of keyboard makes the user more confident about their performance and type longer chunks. This leads to more delay of observing and correcting the errors. And this phenomena is called delayed error correction, and means that the users has to deal with longer text editing and text re-input during the typing process. This also requires more proofreading. So in summary, we provide this high-quality dataset about finger and eye movement during typing on the mobile devices. From this data, the most interesting finding is that attention plays an important role in the typing process. So the different areas on the interface compete for attention. And this kind of computation is more intense than on the physical keyboard. And apart from that, how the users use their attention resource also affects the typing speed. But this is a complex question to answer. We are also conducting a study about super fast typists and trying to find out the answer. So, although we did a lot of data analysis in this study, here we still have so many details don't know about typing behavior, and these details and behavior are all hidden in this dataset. And this dataset provides the possibility for answering any questions you may have relates with typing on mobile devices. You are welcome to download it from our website, and you can also find the link in our paper. Thanks for listening.
Thank you. Thank you. All right, big round of applause for Xinhui. All right.
Sorry for
I suggest we run a little bit into our coffee break, if people don't mind, because I'm sure we have some questions for Xinhui. As with the previous talk, any question, please post on chat. I can kick this off because I'm really interested in this is a very challenging problem of studying eye-hand coordination, in particular on mobile devices, because we know that eye tracking, in particular with portable eye trackers, suffers from accuracy limitations. And then in this context, you have a very small target device in the visual field with the phone and the keyboard on the phone. So I was wondering, could you tell us about how accurate your eye tracker was, how you assessed this, and how any limitations in eye tracker accuracy might affect observations?
So for this eye tracker, we use the SMI eye tracker, and the accuracy of this device is 0.5 degree. And we are using the devices and synchronize the eye tracker, the motion tracker, and the smartphone together. And gaze point has to be mapped onto the, yes, and the sampling rate is 60 Hertz. And
Xinhui, my question is more
30 fps for the field. Sorry?
You note the accuracy. What you mentioned there is what the manufacturer reports, but my question is more about what accuracy you actually observed in the study.
For this one, actually, it's really hard to say that the accuracy, because the eye don't have to be on the target to see it. So in case it's not, there's any question or problem, you select it. And then we see that the typing behavior is really, let's say that according to the typing nature that we can understand. And this is like we need to transfer this gaze point from this field wheel to the smartphone screen. So we need to put some markers on the screen, and also use some technique to transform them. So basically, from the video, we see that it's stable and nice.
Okay.
And anyway,
right. Thank you.
Our interest, the areas of interest, and it's basically divided by the text input area and also the keyboard area. It's not like point something like this.
Okay, I understand. We have a question from Elina. So Elina, if you unmute to ask your question.
Yes. So did you ask how the users normally type with 1 or 2 hands, and any estimate how much the typing with unfamiliar way affects to the eye coordination?
So what do you mean by unfamiliar way?
Well, at least I have this kind of one way of typing. If you request me to type with, for example, 2 fingers in the study, it might affect my eye coordination, because I'm not familiar to type with 2 hands.
Yeah, basically the finger key mapping is kind of fixed for some user who is really familiar with one way of typing. So if you force them to change to another way, then they have to learn this kind of using this finger to find the key. And so we choose typing because these 2 ways of typing is most frequently used during this daily life. And we didn't hear from the participants. They say they are not familiar with this or anything complaints So I think if the typing method is really not familiar to the participant, they might frequently check the keyboard and guide their finger to the keys in the process of typing.
Yes, thank you.
Yeah, thank you very much. Let's thank Xinhui again, and in fact all three speakers in this session. We're now 5 minutes overrun. We should go and get our coffees and teas or whatever. So big thank you again, big round of applause, lots of knocks. Okay, so the next session.